This thing on. Hello, flat earth researchers, debaters and debunkers. There's a little chat while I drive off to pick up my daughter, and just reflecting on the usual kind of trolling that I get from, well, I suppose those that are maybe new to a mixture of those that are new to the flat earth, those that have been trying to debate it a long time, and you still get the same old assumptions. So it's always good to go back and try and clear up a lot of those assumptions. And of course, one of these aspects of believing that we live on a globe is that throughout our schooling, we've been fed these breadcrumbs. Today I was doing some homeschool stuff, teaching my kids about, originally I was going to talk about buoyancy and density and Archimedes principle, but then I just ended up kind of focusing on volume, really, and just the fact that when you're doing volume, you're doing area and then giving it some height. And then explaining that milliliters is what fills, is the same as cubic centimeters, and so on. You see, if you think about the very structured way that we're taught math, and it makes sense, from the units, the columns, the squared paper, the columns, the units, the tens, the hundreds, the thousands, and then the decimal points, and then the tens and the hundreds and the thousands beyond that on the other side. Working out multiplication and things like that. So, and of course, if you have the methodology for doing the multiplications, the algebra, I suppose, then you come across later on. You then come across problems where just part of the solution is to then, for example, finding out the volume of something. You might end up with you've measured something. So I was teaching my kids the difference between making a calculation and making an actual measurement. So you draw the cube on the board and you say it's got this dimensions, and so you're explaining, and then okay, that's a calculation. I've imagined a box, and I've imagined that it's 10 centimeters long and 5 centimeters wide and 2 centimeters high, and I can then imagine or calculate how much volume it would hold, and then we can test that with some. Hang on, I'm talking while I'm trying to work out where I'm going. We can test that by actually doing it. So I got some water, and we had a measure of water in a jug, and we could fill up a box with certain dimensions. So there's a difference there. There's a perception. There's something that you can calculate based. And of course you're using the same calculations to make a prediction. So of course, fundamentally, the mathematics works, and it's a very handy tool for calculating a model of whatever you like, but also actually applying that to a practical reality. So all good, really, isn't it? That's how they all tie in together. So of course that's where the confidence comes from, that you make up a mathematical equation that works. I'm not sure what this woman wants to do. Okay, I'm going to overtake her. And of course the maths can prove itself. You've got your thing, you do your multiplication, and then you can check it with whatever it resolves itself, and that's the beauty of mathematics, isn't it? You get this for people with OCD, they get resolution, they go through the equation, and there's it fits, it works, okay, and there's an element of satisfaction there. But of course, then you've got, for example, the volume of a cylinder. So of course you have to learn how to add things up and multiply, and you're working in units of tens to teach you about the metric system. So the metric system is very, very handy, breaking everything down into units. And Yeah, for example, you start by you learn how to do calculate or measure area of a surface, and then of course what you're doing with volume is just you're stacking those areas on top of each other in layers of centimeters or whatever. Try if you can kind of get that across to that's how that you clarify. So anyway, all this stuff I'm talking about is basically these breadcrumbs which lead you to be able to work out solutions. But of course, what's happened with that is that these have been applied to, for example, dropping something. Now, of course, Newton, throughout history, we have Archimedes, and we have this familiar story that goes with Archimedes. You've got these branches, the buoyancy. Now, because he talked about a buoyant force resisting a downward force. Whether he called it gravity or not, who knows? But of course, there is a downward force of the mass and the buoyant force. But of course, the story goes he was talking. He wanted to know about displacement. He was trying to find out the volume of something, a crown, to see whether it really constituted gold. And I suppose if you had some idea of the density, the dimensions of gold versus silver for particular densities, so he had his eureka moment. But this is just one of those stories. You've got this image of a guy running down the street naked, shouting "Eureka, Eureka!" And boom, the story's in the head. It's a breadcrumb, and here is something that we use in our practical reality: displacement, and it's relative to density, and you have these equations of opposing forces, and so on. All these mathematicians and people throughout history that we're taught about, they of course build up this picture or contribute to a picture of having us working out, because we're smart creatures, that we live on the outside of a spherical Earth. But of course, again, what you've got to understand is this is modeling. So one aspect of that is this idea that mass attracts mass, and that a falling mass, Newton's apple per se, is being attracted to the center of a spherical Earth. Now, this is an assumption of the mechanics of what's actually causing the object to fall, and being able to measure the rate of acceleration is cool, and it's maybe predictable, and there are scientific ways of doing that, and so you're able to describe what's going on, and you'll be able to make calculations, and you're able to say, well, an aircraft that has this much weight, has this much gravity pulling down on it in the medium of air, put it into water, and the buoyant force is pushing back, equalizing it out. Now, mathematically, it can all work out, but that doesn't prove anything of a cause and effect. It proves your description it fits. You found a way to describe the physical properties of what's happening, but it doesn't fit what's actually happening. It doesn't mean there's a pulling force that carries on pulling through the water and pulling the thing down, and that you have this opposing buoyant force. The medium has changed, the ratio of density has changed, or the relationship of density has changed, and again. So what's triggered this is, of course, someone coming to me, thinking they're teaching me the same old stuff that we all know and we've heard, the breadcrumbs about gravity. This step towards. So for a while, I suppose they had this spherical Earth theory or presupposition. This is the thing, isn't it? Presupposing certain things. You presuppose a sphere. And so, really what Newton did was he didn't do anything apart from a thought experiment, just like all the rest of them, and found a way to mathematically describe this, and and then, assume that it's the mass of the Earth. Of course, having a spherical Earth makes it kind of handy for the equations. You've got an even surface. Rather, if it was a square, you'd have to work out if you're saying that gravity comes from the center, but the Earth is a rectangle or something, then you're going to have this ridiculous thought experiment where gravity either increases or decreases the further away you get from the center. If you're dealing with an uneven or even an even, but maybe what would you say, a non-uniform shape or form. But that's, of course, assuming that the mass creates gravity, creates this downward force. There's absolutely no evidence to assume that or believe that. There's no measurable force flowing through the air and pulling everything down until you put something in the air that's more dense than the air. That doesn't dictate the shape of the Earth whatsoever. But of course, it's well understood that if you know the rate of acceleration, you can say that that's a force, and voila, you can. Of course, you have to say what's generating that force. But it also allows you to. Wow, I don't know if you can see that, but the moon's out, daylight moon, just up there. But it allows you to model it, if that's where I was going. It allows you to do what would otherwise be physically impossible in this model. We know that you can't stick to the outside of a sphere. It doesn't happen in our physical reality. If we met a curve, we would go down the curve just like water would. That's what happens in our reality. So, of course, when someone's arguing about this, they suddenly jump out into this conceptual space where Earth is in the middle of space, and there is no up and down. All of a sudden, there's no up and down. And so they've jumped out of reality in order to argue for this perception that we live on a spherical Earth and we're stuck to it because of gravity. It's physically impossible. It doesn't happen. There's nothing to represent that in reality. And so this is why you always come back to that argument. People point at the stars and the this and that. They point at the stars because they believe that this notion of gravity, basically being able to measure the rate of acceleration of a mass falling through the medium of air, allows you to then extrapolate that gravity, and whatever you assume is the cause of gravity, is what keeps planets, including us as another planet, another assumption, going around the sun. Or going around, whatever. Let's just keep it to the so-called solar system for now. But it's all dependent on this so-called force of gravity. Again, the concept is perfectly understood, but what anyone is ever doing is measuring time. The time it takes for these bodies to pass. And again, when you're measuring the rate of acceleration of something falling, you're measuring time. It matters not what the mass is. If it's a 1 kilogram or a 10 kilogram weight, it's still going to fall at pretty much the same rate of acceleration. It's an increased mass doesn't necessarily make it faster. So there isn't more force being created, really. Of course, you're going to factor in wind resistance and things like that, but essentially what you have when a mass falls through the air is just that there's obviously a point where it's compact enough to just fall through the air. Of course, a ton of feathers and a ton of lead weighs the same, but they take up different volumes depending on whether you press them together and there's all these other variables to consider. But essentially, the heavier an object is, it doesn't mean it accelerates faster when you drop it. Okay, so that's a clue. But again, that's one thing. So of course you also have the presupposition of curvature. Doesn't exist. Only exists in drawing. Does not exist. So the fundamental discovery or measurement that should lead to any further scientific exploration is that curvature, rather than And this is why they come at you with all of this, everything. They come at you, oh, look at the stars, look at navigation, look at the celestial sphere, look at orbits. Anything but a fundamental measure of curvature, because it doesn't exist, never has existed. So that's what should happen in the scientific method is you make an observation. Oh, there's some curvature. There's an ocean with a curve. Hang on a minute. The horizon is curved. Well, let's do some calculations. Let's, and then you can, wow, actually it turns out that this curve that we see is part of a sphere. My word. Yeah. But no, that didn't happen, did it? No one ever saw or measured curvature. Yeah. Oh, I don't know what's happening here. You got the police on duty. Maybe a little bit of an event going on, or I don't know, who knows. I'm going around this way, and yeah, that's where I'm going. Yeah. Maybe some kind of event. Yeah. Yeah. So, sorry about that. Lost the satellite signal. Lost the satellite signal going through the urban streets there. You still there? Still there. Yeah. So, it's funny, isn't it? The one thing that you need in order to make any other hypothesis is curvature on the Earth. So I was trying to explain that water. It's funny. Water. It's funny, and it. People don't get it. This is why I titled this. It's simple. It's really, really simple. But we get, and I'm sure if you're a flat earther, you remember going through all of these little explanations about the stars and the planets and this and that and gravity, and you go back through it, you read the planets and this and that and gravity, and you go back through it, you revisit what the stuff they were trying to ram down our throats, the breadcrumbs they were trying to leave a trail of in school. And of course you believe that we naturally, as an intelligent species, came to the same conclusion that Earth must be a globe because of these scholars, because of these mathematicians and their models. But it's completely the opposite. You see, they created a model and then tried to come up, and then you had to come up with explanations to try and fit reality into the model when it doesn't fit. Rather than observing reality in the scientific way that you're supposed to do, you make an observation and then you form a hypothesis. Okay, so we observe curvature, and now we're going to form a hypothesis. We're going to say that curve is part of a bigger curve. Might be a semicircle, might be an arch, it might be wavy, might be part of a wave, it might be a sphere. Who knows? But so what we got to do is then we got to find this curve everywhere, all over, everywhere you look, there should be curve. Only then can you start assuming that the Earth is a ball spinning around in space, around the sun. Yeah? And then you can say, well, hang on a minute, how can we be doing that if we don't actually feel it, or there's nothing to tell us that I'm in Phuket here and I should be perpendicular almost to someone standing up in I don't know, in the UK or something, or the Netherlands or whatever. Yeah? How can you prove that? You go ahead and prove that my down here in Phuket is perpendicular to someone's down near the North Pole. Oh, look at the stars. It's because you can't see the North Star. The North Star's on the horizon, so that means you must have gone round a bloody curve. That's all they've got. They don't have a measure of curvature. They have explanations dreamed up to fit a model that have no basis in reality apart from what you can see in the sky. It's nuts, it's ludicrous, it's mental, yeah? But they got you thinking you're smart. Now, if you think of a crime movie or something like that, you know, a smart criminal is going to leave breadcrumbs. They're going to deliberately not leave any evidence of their crime. They're going to plant bits and pieces that will send you, you know, off on a trail, or threat somebody. So, he did it. Yeah, that's what the smart criminal does, isn't it? And then, you know, why would they lie? Well, the reason that a criminal might lie is for all sorts of reasons, but they do. People lie for self-preservation or for some kind of profit or advantage, whatever it might be. It doesn't matter. People commit crimes all the time. And at first you can see that a crime's being committed. You can see that something's wrong, but you don't know why. So you start an investigation. And you don't just swallow the first thing you're told by someone highly suspect. Because the first people you're going to go to are the ones you suspect. Yeah? Why would they lie? Who knows? But people lie. And we all know as truth seekers that we will lie to ourselves. That's what we do as people. That's our human instinct. And that's why we end up buying certain things or being, everyone knows how it works, that marketeers know how to get you to convince yourself you need the latest hi-fi or phone or whatever. Yeah. They know you'll lie to yourself and to everyone else for the reasons you need it, because you want it. Yeah. So, yeah, you know, it's quite incredible to try and converse with these people, but it's very laborious because you have to take them back through. If they're not willing to do it themselves, you can't really drag them back through either. But you've got to try and point out that what you've been told was a little breadcrumb, a little clue to make you think that you're smart to work it all out. But all they're doing is confusing the issue between reality and perceptions. Now, so as I was saying, the way that maths is taught, it is cleverly kind of done. It's structured in a way that, as I said, it's okay. Professional people have put these maths programs together in school. There's a progressive way you learn how it all works. And if you can master that, the methodology, then you can go through when you're, as I was saying, the difference between you're given a math question. Okay, you want to work out the area, or you want to work out the volume, or you want to work out the circumference, or the perimeter, or the area of the circle. There are, you just have to remember the steps you got to take. But then playing around with the numbers in units of 10 isn't really that difficult. It's just a case, but the thing is, it has to make sense. And actually it does make sense. But what happens is you've got different teachers throughout, they all pick up one after the other. No teacher really explains to you why they are teaching you these steps in order to get, but if you look at it, it is well worked out. I mean, a lot of teachers might naturally just create their own curriculum by going through those steps, but they might not be acutely aware of what they're actually doing and why. Yeah. And that's the thing, that's why maths is horrible for a lot of us, because it's conceptual, and often the way it ties in, or where things fit in to all the other mathematics isn't clearly explained. Yeah, so we just don't. It's like, why are you doing that? And the teacher hasn't prepped with a practical demonstration or whatever. I'm gonna go over here, so we've got some nice sunlight streaming in the window. Yeah. But everything about the globe is presupposed. It's all presupposed for a model. You're always, when you're arguing with globers, you're always arguing about a model. And that's what you have to try and explain to them, is you're arguing for a model, and your model is put together like this, this, and this. Yeah? Let me turn the camera around, put my glasses on so I can, oops, no, hang on, and I'll have a look through the chat there. Oh, let's get you up a bit. Hang on a sec. Yeah. This is great having this. Thank you, Shen, for this little application here. Right. How are we doing there? Who we got in there? Wow. Okay, thanks for all coming in. Zeus got hello. Wow. Okay. Oh man. It's Musicians for Truth. Okay, I'm going to just go with that. That's lovely to respond. I love the interaction. Yeah, Musicians for Truth. Oh, what did you say? All we've done for about 7 years now is readjust all the faulty ratios of size, distance, and density of everything in the sky and Earth. Oh, good. Someone made a point to me today. They're trying to, of course, I'm arguing about the solar, again, lunar eclipses or solar eclipse. They point up at the sky and said, this is because it's predictable. Then it's got a foregone conclusion that's what's going on. But the argument where the shadow of the moon on the Earth during a solar eclipse is you've got your kind of a center bit, and then you've got the shadow around the outside. So basically, what you've got is an out of focus shadow. Yeah, a shadow that's not in focus. So usually on the Earth, you look around. If you look around at the shadows here, they're all have very clearly defined shadows, and so a shadow's clarity depends on its the distance between the whatever it's casting the shadow on and the light source itself. So it's only when you get, like, if my hand is the light source and I'm using this hand here to cast a shadow on the wall over there, then the closer my hand gets to the light source, the more blurry the shadow is going to be over there. Get it further away from the light source, or at least there's a distance, there's a point, there's a sweet spot where it becomes clear. The shadow over there becomes very clear. Bring this closer to the light source here, and the shadow over there is all blurry. So if the sun is creating a moon shadow on the Earth that is out of focus, it's not clear, then what does that say about the distance between the Earth and the moon? It means that the sun is very close to the moon, and so the shadow that it casts on the Earth is a blurry, out of focus shadow. Whereas if there was an equal distance between them, if there was a greater distance between them, in fact, that would say to me that the distance between the moon and the sun is not even as great as the distance between the Earth and the moon. So that's what they say, it's 250,000 miles. So it means that the distance between the moon and the sun is less than 250,000 miles, because if the shadows of the moon on the Earth are blurry and out of focus, which is only a result of the source of the shadow being close to the light. Yeah. Either way, just because we can predict eclipses and use circles to make those predictions, because you're talking about time, a clock, you can say, okay, it's going to come around in another 12 hours or another 24 hours, but it's going to be slightly off skew until these two meet, blah blah blah. Doesn't determine the shape of the Earth at all, does it? Yeah. Right. I'll go back up from the chat. So man. Oh gosh. Oh, my battery's running out, I think. Yes. Okay, guys, we'll have to get back to this later. Let's say goodbye before this cuts out. Okay. Thanks very much for coming on for the ride. I'd love to look back through the chat. Hopefully, it's something that I can make another video on with that's a bit more concise. But for now, take care. Speak soon. Okay. Cheerio.